in Python language. Give him a warm welcome.
Okay, hello everybody. I'm Peter, and some time ago I was asked to help with some aspect of the CPython interpreter regarding module loading, which meant I had to learn a lot about how imports work. So, changing something is the best way to learn, and what I learned, I will now tell to you. So when you have to do something regarding imports, you don't have to rediscover everything from the basics. So this talk is about what happens when you import some random module. It's kind of like the famous interview questions, type python.org into the browser, what happens? There's some DNS and contacting servers and HTML and JavaScript, CSS and stuff like that. It's all very complex. And this simple statement is also similarly complex. Now, when I prepared this talk, I learned that there are other talks and workshops like this. David Beasley did a really good workshop at PyCon US this year. If you've seen it, I hope I can give you some more information even than that. If not, you can watch it afterwards if you're interested. So some of the things I wanted to talk about, I will not talk about because they're better explained there. But you will still find this useful, I hope. So instead of a real deep dive, this is more like a guided tour of the main things that happen when something gets imported. So we have this simple statement. What does this actually do? Well, this gets compiled into some bytecode, and the bytecode, when executed, does a very simple thing. It gets a global function named $import, and it just calls it and assigns the result to a variable. It's pretty simple, right? Things can get more complex. You can do stuff like importing from the current package like this. And again, what happens under the covers is this gets mapped to some call of the import function and getting some attributes from it and assigning it to a variable. This stuff is hard to wrap your head around. It's explained pretty well in the documentation. But the good thing about it is you don't really have to worry about it. Now, this is an implementation detail. What the import function does is just call the import machinery. What you can do alternatively, you can just call import.import module. So if you ever see the import function in some code, that's the old way to do it. Now there's import module, which has a better API and does pretty much the same thing. These are the gateways to the import machinery. You can forget about that one. And now what does the import machinery do? The import machinery will be explained in this talk. I will not concern myself with the finer details like locking caching, backwards compatibility stuff, all other things that makes this complicated. And if you really need to know these details, then it's better if you just read the code. It's all there. So this talk will just give an overview, give you everything you know to start reading the code if you need the details. All right, so we have this call. What does this do? So if you simplify it, this is what happens. First, we check if the module is in sys.module. Sys.modules is a dictionary that holds a mapping to module name to the imported module. It's a cache. It's pretty simple. what it is supposed to do is make sure that if you import one module more times, you always get the same module back. So, import some module, save it in a variable, import it again, you got the same module back. This means importing module when it's already loaded is very fast, it's just a date lookup. Now, since this is a simple cache, what you can do is play around. So if you delete a module from sys.modules and then re-import it, you will get a different module object. The import machinery runs again, makes a new module object, and gives you that. Forgets that it was ever loaded before. Also, since this is a cache, you can do cache poisoning. So you can actually put anything in sys.modules. Like here I put a string, and then I import it, and I get a string from an import statement. This is interesting to look at, but and you shouldn't really use it, but some modules do use it. What this allows you to do is make modules that have, well, module-like things that you can import and that allow you to call them or subscript them, stuff like that. So this is possible. Not sure if you should use it, but it's possible. Okay, so that's for the cache. The next thing that happens when we import a module is a call to this find spec. And a find spec is a function that finds where the module should be loaded from. That's the reason it's there. It gets the module name and it gets a path. Now the path usually gets loaded from sys.path, which is just a list of all the directories where Python modules live on your computer. There's the current directory, this here, and then there's a whole list of system modules, user modules, pip install modules, all the directories where you can load those from. You can add things to sys.path. So if your modules are stored somewhere else, you can simply put it here. Now what find spec returns is called a module spec object. Now this is a record of all the things you need to load the object. So it tells you what the name of the object is, it tells you how to load it, the mechanism for loading, it tells you where to load it from. So if you ever need these details about a module without actually loading it, you can just call find spec, it'll return you this. Here's another example. We have the IO module. It has a slightly different, this one has the same loader, sorry. Yeah, so it Gantt gives you an origin. So if you want to find where a module is located on your file system, call the find spec function. Right, now that we know where to load the module from, we actually load it. This function is pretty simple, but to simplify it even more than, to simplify it a lot, it does two things. It puts a module object in sys.modules, and then it initializes it. Initializing means it goes through what's in the module and it executes it. So, first put a blank object in sys.modules, and then fill it up by executing it. This actually gives you enough to reason about what happens when you have circular imports. If you have two modules that import from each other and try to use whatever they imported, you might run into trouble. So let's see what happens. Import foo.py. So when importing foo.py, we check if it's in sys modules yet. It's not there, so we go on. You find where to load it from. We load it, which means we put the blank module in sys.modules, and then initialize it, which means run through what's written inside and execute that. So the first statement is import bar, So we run the import machinery again. Is bar in sys modules? Not yet. So we find where to load it from, put a blank bar module in sys.modules, and run through this. So the first step is to import foo. How do we import foo? Is it a sys modules? Yes, it was put there by the load step before starting to execute this. So we skip this and just return the foo.py, which is currently blank because it didn't set the function yet, didn't get to this function. So we try to use the function from foo, which is not there yet, and we get an attribute error. This is a common problem. Beginners get it very easily. The solution is to not do circular imports. You will always want to have a tree of your imports, not have any cycles. So, after loading, we get the module from sys.modules again. This is for the case when a module itself poisons the cache, replaces itself in sys.modules. You can do that, it's not recommended. And then the module is returned. Things get a little more complicated if you have submodules. So what are submodules? If you have a normal .py module, it's in a single file, everything's simple. If you have a directory with more files, you can have it under init.py, which acts like the package itself. And then you have submodules, which you can import from the package. So you can import urllib.request, and it looks into urllib directory, and gives you the request module. How exactly does this work? So first of all, the path here is not taken from sys.path, but it's taken from the parent module. So each package has an attribute called underPath, which lists all the directories the submodules are loaded from. So submodules of urllib are loaded from here. And then what happens is there's some extra logic for submodules. First of all, when you're importing a submodule, the parent always gets loaded first. So there's no way to import urllib.request without first importing urllib itself. And if that has a side effect of loading the actual submodule, then it's just returned here. And after everything is done, the submodule gets assigned to an attribute of its parent. So this gives you urllib.request. If you have the urllib variable, you can use urllib.request. Right, and this gives you a framework to think about when analyzing circle imports with sub-packages, which is very confusing. And this is kind of how it works. We have an init.py, which imports stuff from main and const submodules. We have a main which tries to use some value from the const. And that doesn't work. Why doesn't it work? Let's walk through again. So we try to import foo.main, for example, which always imports the parent module first. So we have init. Is that in sysmodules? Not yet. So we find where to load it from. We load it, put a blank module in sysmodules, and run through this. Now we start importing main. So we go here again. Is foo.main in sysmodules yet? No, it isn't. We try to load the parent module. That's already in sys.modules, so that's already done. We find where to load main from, and we start loading it. We get to import foo. That's already in sys.modules, so it is imported directly. And then we try to use foo.consts, which it doesn't exist yet because consts wasn't imported from the init yet. Right? So this piece of code is all you need to analyze circular imports. It's in your little booklet or it's online if you want it. It's pretty simple and pretty useful if you have some gnarly package you need to analyze. If you're writing a package from scratch, these are the rules you should follow, and if you follow these, you won't run into problems. So, and it should import from submodules, optionally set all, and do nothing else at all. Everything should be in the submodules. And the submodules should not import directly from init. They should know where the actual thing they want is in. And of course, they shouldn't have internal import cycles. All right, so now that we have the basics done, let's look a bit more into this find spec. What does find spec do? It finds where to load a module from. So if you import random and look where it is and you just print it out, it tells you, hey, it's loaded from this file. Pretty simple, right? It's stored in the file attribute, all there. If you import sys and print it out, it says built in. You know, there's no file on your file system that corresponds to the sys module. There is no Dunker file attribute on the sys module. Why is that? Does anybody know where the sys module is on your system? Well, Nick knows it, of course. Yeah, that's why he's a core contributor. Yeah, so this is the location of your sys module. It's inside the Python binary. It's compiled in. Right, so there's no extra file. It's actually inside Python itself. We have this little zoo or aquarium of kinds of modules. So we can have built-in modules, which are written in C, compiled, and inside the Python library, Python binary itself. We have source modules, which are written in Python, and they live in .py files. And we can also fill these other squares. So we can have compiled modules that are loaded from files, from shared libraries. You can configure Python to build math this way. So it gets pulled from an external file, but it's actually written in C. And you can have frozen modules, which are written in Python, and the bytecode is inserted into the Python binary. There aren't too many like this, but if you're compiling Python for embedded systems, for example, you can just compile your Python modules in. And also the import lib itself is frozen because you need import lib to open external files, so you import lib inside Python itself. Right, so how do we load all this? There's this variable called sys.metapath that tells Python what to do when a module is imported. What find spec does is just go through this, and when it finds something for the module it's loading, it calls its find spec method. So if I'm loading the sys module, find spec goes through sys.metapath and it says, hey, built-in importer, can you load a module called sys? And the built-in importer looks at the list of built-in modules and finds sys in there and says, yeah, sys is a built-in module, so it just returns that. All is nice, all is fine. If I try to find the random module, it goes through the list, so it has built-in importer. Is there a built-in module called sys? No, there's not. Is there a frozen module called sys? Probably not. Well, sorry, not sys, called random. So is there a built-in module called random? No such module. Frozen, it's also probably not frozen. So it goes to Pathfinder, and that's where the fun begins. Pathfinder looks for modules that are in files on your file system. So it actually looks through sys.path. And the way it does that it goes through the list, and for each for each directory, it constructs a path hook object and asks that to load the module. So for random, it goes through the current directory, asks a zip importer if it can load from the current directory. It probably can't. It goes to some zip file on the path, asks a zip importer if it can load from that, and it can, but there is no random module inside the zip, so it goes on. And then it gets to this path, adds a zip importer if it can load from that path. It can't, so it constructs a file finder, which can import from there. And the file finder will look inside the directory for appropriately named files with these extensions we can load from. It sees a random.py, so it knows, this is a source module, you need to load this from source. If it was an extension module, it would have a different extension. It would tell you to load it as an extension module. Does that make sense? A little bit. Okay, yeah, so this is as simple as I could make it. There's two for loops, and you look through metapaths, path hooks, and sys.path. These are all points you can extend the mechanism at, so you can add your own metapath items, you can add your own path hooks, you can add stuff to path, and it all works out, and also is backwards compatible. Right, so now what does the find spec return? What is this module spec object that it returns? It's a very simple object. It just has attributes, which usually are just strings. It has a name, an origin, which is where to load it from. It can have a cached attribute, which tells you where bytecode cache is located for speeding things up. It gives you the loader object that you can call to actually load the module. And then it can have some state for the loader, which is not really used too much. It can give you the parent of a submodule, and it can give you where to look for submodules. So now that we have find spec done, we can look what happens in this load function. So the load function is actually pretty simple. The first thing that it does is it creates a module object. Usually it creates something called a module type object, which is just the normal module object. It is not very special, it just has a name and a special type. But extension modules can override this and define a create module that returns a different kind of object. In Python, you can't do this. You have to resort to hacks to put a different object in the cache. So you create an object, then it sets the initial attributes of the module. So it pretty much copies things from the spec. So it assigns the spec to something called underspec. It assigns the name, assigns the loader, and it assigns all these to module attributes. Probably most of you know that module attributes can be used as variables. So if I'm in the interactive prompt, all the variables I'm working with are actually attributes on the .domain module. So if I import the .domain module, I set a variable to something, I can find the variable as an attribute on the module. And if I set an attribute on the module, I can then use it as a variable. So this is why if .name equals .main works. the name of the module from spec.name is set to this module attribute, which becomes a variable. And the main module is always named main. Right, and then what happens is exec module. What that does, it finds, it reads in the file with the source and just goes through this in the context of the module. So any variables in that module that you define become attributes on the module. So if you define a function, that function is assigned to a variable, which means it's assigned as an attribute to the module. This can be summarized in the do steps I told you before. Put an empty module in sys.modules and execute it. So this part is pretty simple. The part that is not that simple is how you actually get the code to execute. This is complicated a bit by the presence of PYC files, by the cached bytecode files. So what happens is if spec.cache, this PYC file exists, and inside the file there's a modification time and some metadata that should match the py file it's compiled from. If that matches, it means the cache is current, so it just uses compiled bytecode and executes that. If that doesn't exist, or if it doesn't match, it loads the file from origin, the actual py file, compiles that into bytecode, and then tries to write that to the PYC location. If that fails, doesn't matter, just skips this step. Why this is done, bytecode compilation can be a bit slow, so it makes sense to only do it once and cache the results, so imports are faster next time you do them. This is a part that changed visibly from Python 2. In Python 2, you didn't have this dunder PyCache directory, and the PYC files were stored right next to the py files. So Python 2, you had a directory that looked like this. And what could happen is if you delete the py file, the PYC would get loaded. So it was like there was a ghost of a module that existed before, but you delete it and it's still there. What happens in Python 3 is there's a PyCache module, and if you delete the py file, then it doesn't get found at all. The find module only looks at the py. So it doesn't get found at all, and PYC is never checked. If I go back a bit to here, you can see that the pathfinder only looks in the actual directory the module should be in. So if there's a PYC there, it can return that, but PYC is not there, it's in a dunder PyCache directory, so it's not found here, and this PYC is not even considered. What you can do is copy this PYC file to the top, to the one directory up, and then gets used. Right, so that's pretty much all you need to know about imports. How imports work, how to deal with import loops, stuff like that. I'm a bit early, so if you have any questions, I'll take questions now. If you don't, I can add something to this presentation.
I was hoping you'd tell a little bit more about how namespaces work, because this is going to the next complication level.
Namespace modules, namespace packages. All right. Okay. So there's going to be a live demo now, so let's pray it works. The way... okay, thanks. The way... yeah, I will. The way packages are loaded is... where was this? Yeah, I neglected to tell you that in addition to these, it also looks for random/dunderin.py. So it looks at a directory named after the module and a dunder init there. So if I create a package and put a dunder init in there, save it as dunder init, and then in here I can import package and it should work. Yeah, that imports a package. I can put submodules in here. So I'll name this foo.py and import package.foo. What that does, first it imports the parent module, then it imports the submodule. Now what you can do now is you can actually remove this init.py and oh, I thought I had the virtual env ready, sorry.
You ran it under Python too.
Never run stuff under Python 2. That magic number, whatever. Yeah, okay. There's a solution. Never do live demos, of course. Anyway, so this works without an init.py. Why does that work? Now, there's a reason for it, but I'll first explain how these things work. Python looks for all the directories, and if it finds init.py in one of them, that becomes the directory for the package. So if there's one under init.py, only that is taken as the directory of the package. If it doesn't find under init anywhere, then it combines all the directories it looked through and makes a namespace package out of them. So I can have another directory and I can have a package in there, and I can have a bar.py module in here. And in demo, I can import package.bar, and I have to add this another directory to my Python path. So now it works. Right? So my Python path is the current directory and also another directory. So Python goes through everything on the path, finds one package directory in here, another package directory in here, and combines them together. So
PY in the another directory package?
It would use the first one it finds. So interactively, I can import package, look a bit more on that. It says it's a namespace module, name package. It has the list of directories it loads from, so it loads from the current directory /package, and loads from another directory /package. If I add another package somewhere, it will actually pick this up because this is a magic list object that responds to changes on your file system. So why is this done this way? I can personally only see one use case for this, which is plugin registration. So if you have, for example, an audio editor, and you need some effect plugins for that, you can install them system-wide to user lib somewhere. You can install them to your user directory. You can have them in your current directory if you're working on them. And if it's a namespace package, then it combines all these locations and gives you all the plugins you have installed anywhere. Right? Before these namespace packages were added into Python itself, there was a hack involving an init.py that had to be the same in each of these directories, so it wouldn't matter which one is loaded first. And it would manually change the path of the package to include everything. Now Python does it by itself, but it's also a bit confusing because if you leave out init.py anywhere, magic happens.
What if our package init.py and we still want to add some submodule to it as a namespace? It's not separate.
Okay, the question was, what if the package has init.py but you still wanted to add submodules to it?
Yes.
Python doesn't do that automatically. What you can do is, if I bring back my init.py, I can say path dot append
But this is the original package. Yeah,
Right.
The first one. What if the original package has the init.py? For example, it's Django, and I still want to add to Django.python. I know it's possible.
So would the original package has a python.py, but you want to add another path to it?
Yes. Let's say I have a Django package. I installed. It's not mine. I cannot edit it, so I cannot add. I cannot append to path from this package.
Right.
But I install, for example, an extension that
Right,
I want to leave under Django.net.
Okay, so
Well, there is something.
you can also, monkey patch the path before you import the modules. Is that what you're asking about? I'm not sure if I'm getting the question correctly.
I'm not sure whether it would work.
This is another directory.
I know it's possible to have like init.py in your another directory package.
Right.
In that init.py you have to have some line regarding namespaces.
Right.
Register under the namespace of package.
Yeah. That's what I was doing here. You can just append to the path, and then for submodules it will look into the paths.
The original package. Let's say I do not have access to it. I'm not the owner of the original package. I want to add a submodule, an extension.
Okay. Yeah. Please come to me afterwards because I think I'm not understanding you correctly.
Okay. Okay.
And let's not waste other people's time with, getting through to me.
Maybe I have an idea. You want to extend a package with the names by using a namespace? Something like that?
Something like this. Yeah, but let's talk
So you
about
have already existing package and you want to extend it, but not by defining exact same package, but by using the namespace that will fall into the same package.
Oh.
Let's talk about this later.
Let's talk about it later. I don't think I'm getting your use case. But Nick is getting it.
Yeah, declare namespace, yes.
It's deliberately not supported. The original package has to, like, you can do it with monkey patching, but the original package has to say, yes, I'm a namespace package, either by using none.init or by using the package util.extend part stuff.
Sorry, but I disagree.
No.
Let's talk about this later.
We did it on purpose. We had the choice to make things always namespace packages, and we decided not to. That's PEP 420 is the one that does it.
works in Python too. Maybe by mistake.
No, we deliberately chose not to do it.
Well, that choice I think was made to make it safer. You have your package somewhere and it has a dunder in it, so you always knows that it is only this package and it can be modified from elsewhere easily.
Do we have more questions for Peter? If not, thank you very much, Peter.
Okay.
Don't forget to get your votes. Green, okay, perfect. Red, didn't like it. White or yellow. And the next presentation will be in about 15 minutes.